Hi, in this video we are going to talk about spanning trees, so let's get started. What is a spanning tree? A spanning tree of an undirected G graph is a subgraph that includes all the vertices of G. In general, a tree may have several spanning trees, and we can assign a weight to each edge, of course. A minimum spanning tree is a spanning tree with weight less than or equal to the weight of every other spanning tree. Has lots of applications, of course, in big data analysis, clustering algorithms for example, finding minimum cost for a telecommunications company laying cable to a new neighborhood. As far as clustering algorithms are concerned, I have to admit that the k-means clustering or hierarchical clustering relies on a different algorithm, but of course that we can construct if we have a very lots of vertices in a very dense graph. Then of course we can construct a clustering algorithm with the help of the minimum spanning trees that are very efficient. But for example, k-mean clustering and the machine learning algorithms are not using these minimum spanning trees as far as clustering algorithms are concerned. Okay, so the standard algorithms for finding minimum spanning trees are Prim's-Yarnik algorithm and Kruskal algorithm. Kruskal algorithms, these are greedy algorithms, as we have seen in Dijkstra's algorithm for example. So it tries to find the global optimum with the help of greedy local minimum searches. So let me tell a few words about Kruskal algorithm. We sort the edges according to their edge weights. We can do it, or it can be done in ordo n log n time complexity with merge sort or quick sort, or we have seen so far that heap sort has a n log n time complexity, so we can done it very quickly. Or if you are familiar with, for example, radix sort, the string sorting algorithms, we can do it even in linear time complexity. And of course, Kruskal algorithms relies heavily on this sorting algorithm. Union find data structure, it's very important, it is the disjoint set. We are going to see the illustrations that it's very important that we have to detect cycles, whether adding a new edge will form a cycle or not. So we start adding edges to the minimal spanning tree, and we want to make sure there will be no cycles in the spanning tree, and it can be done in ordo log v with the help of union find data structure. So why is it good to construct union find or disjoint set? Because it's going to make sure that Kruskal algorithms is very fast. And of course this ordo log v, in this formula the v denotes the number of vertices in our graph. We could use a heap instead, sorting the edges in the beginning, but the running time would be the same. So sometimes Kruskal's algorithm is implemented with the help of priority queues. We see that, for example, min heap, we have to construct a min heap, and the root node will be the and if we construct this priority queue according to the edge weights, then the root will be the edges or the edge with the minimum weight, and that's what we need. So it is an alternative for solving the problem, but the main approach is to sort the edges according to its weights with the help of the divide and conquer algorithm such as merge sort or quick sort is the best. Okay, so worst case running time is ordo e log e, where e denotes the number of edges in our graph, so we can use it for huge graphs too. If the edges are sorted, the algorithm will be quasi-linear, very fast. If we multiply the weights with a constant or add a constant to the edge weights, the result will be the same. In physics, an invariant is a property of the system that remains unchanged under some transformation. I'm qualified as a physicist, so I'm interested in these kinds of symmetries. And if you consider, or we can come to the conclusion that lots of for example, energy law can be reduced to symmetries, so these invariant properties are very important in nature. But anyways, in the Kruskal algorithm, edge weights are invariant under the transformation of these weights, addition and multiplication. Yeah. So let's see how it operates. We have 1, 2, 3, 4, 5 points and 1, 2, 3, 4, 5 edges, each with different edge weights, and we want to construct a minimum spanning tree. We sort the edges according to its weight, so we start with the lowest, and the lowest weight is 2, so we keep adding it to the minimum spanning tree and have to make sure that adding this edge won't form a cycle, and it's not going to form a cycle, so we add it. Then we add the next one, which is 3. After we have sorted these edges, then the order will be 2, 3, 4, 5 and 6. So we have added 2, we can add 3 without forming a cycle. We add the next one 4, and in this situation the next one would be the edge with cost 5, but you may come to the conclusion that it may form a cycle, because if we connect 1 with node 5, then there's a cycle, so we have to skip this edge and we have to add the next one. So we added 4 and we have to add the 6, and the total cost is 15, because 2 plus 3 plus 4 plus 6 is equal to 15 units. So that's why we have to skip the edge 5. So this is Kruskal algorithm. To summarize, we have to sort the edges according to edge weights, and we have to keep adding the edges from the sorted order to the minimum spanning trees, and we have to make sure after every before adding this edge to the minimum spanning tree that we are not going to form a cycle, and it can be done in logarithmic time complexity with the help of a union, find or disjoint set data structure. Okay. What about Prim-Yarnik algorithm? In Kruskal implementation, we build a spanning tree separately, adding the smallest edge to the spanning tree if there is no cycle. In Prim's algorithm, we build a spanning tree from a given vertex, adding the smallest edge to the MST, and this is why it's a greedy algorithm. We keep adding the edge with the smallest weight. There are two implementations, the lazy and the eager. We are going to see the illustration of the lazy implementation because it's very popular. It's working very good. Lazy implementation add the new neighbor edges to the heap without deleting its content. It's very important. We are not updating the content of our heap. We just keep adding and adding, and it's going to get us the right solution. The eager implementation, we keep updating the heap if the distance from a vertex to the minimum spanning tree has changed. But updating the heap can be very costly because it takes logarithmic time complexity to update and rebuild the heap. So the greedy approach is usually the best. So the average running time is ordo E log E, but we need additional memory space ordo E. Worst case is the E log V, when E is the number of edges and V is the number of vertices. So let's see how it operates. We start from a given vertex, for example the 1, and we consider the edges. We have edge 2, edge 5, edge with weight 2, edge with weight 5, edge with weight 6, and we keep adding the one with the lowest weight, which is 2. And we are not updating the heap. So in this situation, the heap consists of we keep popping the edge with 2, so it's not consisting anymore, but the edge with weight 5 and edge with weight 6 are still in the heap. And we keep adding the edges to the heap, for example 3, and considering which is the edge with the lowest weight, and it is the 3. We keep adding the next edge, which is the edge with weight 4, and we considering which is the lowest. It is 4, and it's not form a cycle. We haven't visited, for example, 5, so we can do it, but we do not add 5 because we have already visited 1, node 2, node 5, node 4, so we skip the edge with weight 5 and we add the edge with weight 6. So that's all about the lazy implementation of Prim's algorithm. And finally, let me consider how Prim's VS versus Kruskal algorithm when to use these algorithms. Prim's algorithm is significantly faster in the limit when you've got a really dense graph with many more edges than vertices. In these situations, Prim's algorithm is very fast, especially the lazy implementation. Kruskal performs better in typical situations, sparse graphs, because it uses simpler data structure. It's very important that Kruskal uses very simple data structures. Kruskal can have better performance if the edges can be sorted in linear time or are already sorted. We have I said that in this situation it's very fast, and Prim's better if the number of edges to vertices is very high. So that's all about the comparison of Prim's and Kruskal algorithm. Yeah, thanks for watching.